Linear motion. When considering linear motion, there are three things we need to consider: the position of an object, its velocity, and its acceleration. A remarkable relationship exists among the position of an object, its velocity, and its acceleration. First, let's get a better understanding of what these words mean. Position is the location of an object in regards to a reference point, which can be its starting location. So you might want to consider the position of a runner after he or she has left the starting line. It may also be the position of a baseball and its position or relationship from home plate to wherever it lands. Velocity is two things. It's how fast and which direction the object is moving. And acceleration is how fast and what direction an object's velocity is changing. It's the same word for how fast an object's speed is changing. So with acceleration, you would want to consider how many meters per second an object is increasing or decreasing per second. So the units would be meters per second, such as a car may be accelerating 10 meters per second every second, and that's often consolidated into meters per second squared. Are velocity and speed the same thing? Although you may hear velocity and speed interchanged often in common conversation, they are, in fact, two distinct quantities. Sometimes they are equivalent to each other, but this depends on the direction of the object. Velocity measures how fast and in what direction an object is moving. For example, if the velocity of an object is negative 3 feet per second, then that object is moving backwards or to the left, that's the direction, at a rate of 3 feet per second, and that would be the magnitude. So if our runner, who has been running forward at 3 feet per second, decides to start running backwards at also 3 feet per second, that would be denoted with a negative. So we would say that runner is going backwards at negative 3 feet per second. So note, the positive or negative direction is determined by the object's initial position and what is determined to be positive or negative direction. Now, speed only measures how fast an object is moving and disregards the direction, thus is always positive. So we can say that speed is equal to the absolute value of the velocity. As we discuss position, velocity, and acceleration, it's important to go over some important notations, as each has a common notation used in calculus. The position function, for example, will be denoted with an x of t, or an s of t, or p of t. V of t is the notation for our velocity function, and a of t is the notation for our acceleration function. Let's discuss position, velocity, and acceleration and how they relate to derivatives. If given a position function x as a function of t, let x of t equal the position at any time t. The units will be usually meters, feet, centimeters, yards, inches, and miles. Now the instantaneous velocity of an object is given by the derivative of x of t. So x prime of t is equal to v of t, which is the velocity. The units are usually meters per second, feet per second, or miles per hour. Now, for acceleration, that is equal to the derivative of the velocity. So v prime of t is equal to a of t, which is the acceleration. Also notice that since up here, x prime gives you v of t, the second derivative of your position function, x double prime, is also equal to your acceleration. So knowing your original position function, the second derivative will give you the acceleration. The units for acceleration are usually meters per second squared, feet per second squared, or miles per hour squared. Let's discuss briefly average versus instantaneous velocity. It's important to remember or recall that the derivative finds the slope of a curve at one point and therefore represents an instantaneous rate of change or instantaneous velocity. By contrast, to find the average velocity, we would go back to using our slope formula and find the average change between 2 points.